In this video, we'll talk about even and odd functions. So we've talked a lot about different kinds of transformations, vertical shifting, vertical stretching, horizontal stretching, and flipping a graph of a function over the x or the y axes. So the last kind of relevant tool to know how to graph a particular function is knowing whether it's even or odd. So we'll go through a graphical explanation and then we'll go through the formal definition. So let's consider the graphs of f of x equals x squared and g of x equals x cubed. So when we look at these graphs, and we kind of notice that there's a symmetry about them. Certainly in the case of f of x equals x squared, maybe it's a little bit less obvious in the case of g of x equals x cubed, but there is a symmetry to it. And the symmetry is this. For f of x equals x squared, if I grab any x value along the positive half of the x-axis, we'll get some y value out, right? That's the f of x. So we could call this x1, and this is f of x1. That's the y value. And if we grabbed the number that's the same distance from the origin in the negative direction, call it x2, and evaluated f of x equals x squared at x2, we would get the same value. This is f of x2. So we notice that f of x1 equals f of x2. And this is true for any positive and negative number who have the same absolute value. That is, if we try f of some negative x, the y value that the function takes on, the graph, is the same as f of x. Now, if we look at g of x equals x cubed, there's a similar kind of symmetry, similar kind of pattern, not exactly the same, but if we look at it like this, if we take some positive x, we'll call this one, just for the sake of it, we'll call it f, we'll call it a, the y value that this graph takes on is g of a. And if we go the same distance in the opposite direction, if we go negative a along the x-axis, we notice that we get a similar y value, but negative. So now we've got negative g of a. And this is true for any negative x or negative a and positive a. So we could say that for g of negative x, this is the same thing as negative g of x. And we can convince ourselves if we just try a couple values. Let's, for example, try with f of x equals x squared. Let's try negative 3 and positive 3. So f of negative 3, that's negative 3 squared, which is the same thing as negative 1 squared times 3 squared, which is 3 squared, which equals f of 3. You see how this works? And similarly with g of x equals x cubed, you could try it and we would find that g of negative 2 would be equivalent to negative g of 2. A graph that has this property is even when f of negative x equals f of x, and odd when g of negative x equals negative g of x. Even functions, like f of x equals x squared, have symmetry about the y-axis, and we can see that by inspection. If we flipped it about the y-axis, we would get the same graph out. And functions that have the property g of negative x equals negative g of x are called odd and have symmetry about the origin. So formally, even and odd functions, let f be a function and d be the domain of f. F is even if f of negative x equals f of x for all x in D. So I've written this out a little bit differently than I might typically. I want to try to explore some more formal mathematical notation. So this upside down A, that just says for any x that we might choose in the domain D of f. And f is odd if f of negative x equals negative f of x for all x in D. And then I've just drawn a couple graphs so you can see, once again, I've got an x squared on the left, f of x equals x squared, and the graph of an even function has symmetry about the y-axis, and on the right I've drawn an odd function, I've drawn the graph of an odd function, and the graph of an odd function has symmetry about the origin.